Hello, everyone, and welcome. I am Sébastien Sinold, the product manager for the Enea Cosmos probe. And today I will be talking about a recent attack named Sunburst that compromised many US organizations last year, resulting in leakage of very sensitive data from critical infrastructures. I will obviously also discuss about measures that could have been taken to detect such attack earlier. So first, we will detail how this attack happened and what mechanism it used to spread itself across networks. Then we will see what a cyber sensor is and what role it plays in detecting threats to complement the traditional IDS. At last, we will demonstrate a few concrete examples based on MITRE categories to illustrate the added value of a cyber sensor. So first, let us review the Sunburst attack that happened last year, affecting very well-protected critical organizations and business and federal agencies in the US. In the case of Sunburst, malware was introduced through an update on Solarwinds Orion software. Orion is a network management software largely deployed on critical infrastructures. The first stage of the attack was stealing the Solarwinds certificate and then using it to insert the malware code into the Solarwinds update repository. The customers then install the malware-infected update. It will stay quiet for a couple of weeks. So in case the update is first tested in a controlled environment, like a sandbox, for instance, no anomaly is detected. But then after a few weeks came the credential theft and propagation. Orion, being a network management tool, it has access to many credentials in order to manage a large variety of network services. It can access all the accounts and passwords, making it very easy for the malware to gain privileges and replicate itself on various machines. Moreover, the malware was able to hide itself using host names very similar to existing host name of the targeted organization. So security analysts were not able to identify this illegitimate traffic. Those lateral movements mainly use standard network services like SSH or NFS, where the communication with the command and control servers were using the remote desktop protocols, also known as RDP. Those two types of communications appearing legitimate, it evades traditional detection methods from intrusion detection system. So this is the reason why advanced traffic analysis is required to detect such inappropriate behavior. This type of detection is the main objective of a cyber sensors. So here is another view of the Sunburst attack using the MITRE framework to show the workflow of the malware and the variety of techniques used. For each category, MITRE details the techniques a malware can use and what detection methods must be put in place for detection. As you might be aware of, this framework is very useful for identifying and analyzing cyber attacks like Sunburst. Defenses you can use against the various MITRE attacks techniques generally fall into perimeter defenses, here on the left, like a firewall or filtering proxies. But also, internal network-based defenses on the right must be considered. The network defenses are designed to catch advanced persistent threats like Sunburst that have evaded the perimeter defenses. It is here on the right side that the detection capabilities of cyber sensors have a very important role to play. Cyber sensor being passive, it will not prevent from the first steps of an attack. Once again, this is more the role of next generation firewalls or any filtering or blocking systems. But it helps to detect quickly and efficiently a running malware on your network, so countermeasures can be taken before too much damage is done. Let's have a look in details at the role of a cyber sensor for threat detection. The main goal of a cyber sensor is to classify every network flow up to the application level and to categorize those applications. So where a traditional intrusion detection system can detect between 50 or 100 protocols, a cyber sensor can detect thousands of protocols, and could be standard protocol or even proprietary protocol like peer-to-peer protocol, or this kind of tool as well. And this works both from classical IT protocols and OT protocols, like industrial control systems. So it classifies both the user traffic generated by humans, and any kind of connected device of industrial networks. So traffic generated by machines, typically. And aside from this classification, the sensor can also extract a large set of metadata, like sender-receiver details for a connection, or device type. Is it a laptop, a mobile phone, or any other IP device, like a printer or camera? And it also can identify the transaction type. Is it an audio call? Is it a video streaming? Is it a file transfer? Then in case, for instance, for a file transfer, it can extract file details, like a file hashes, a file type, obviously. So the sensor extracts all this kind of information. And then this metadata can be stored into a SIM or any other kind of database, actually. And it provides information almost as complete as a full packet capture, but with very limited storage requirements, maybe up to 150 times less storage requirement compared to a full packet capture. And the reason is because all the irrelevant content, like the encrypted payload, for instance, or the video content itself, can be discarded. Let's compare here the different network data sources that are available today. As a criteria for this comparison, first we're going to use the context. So the context means the level of information provided by the data source. Then the second column is the pivot field, which is the ability to correlate information together from all those different sources. The third column is the retention period, resulting from the volume of the information generated by the data source. And the last two columns are the security rules, which can be split in two parts. The community rules that are open and provided by the community, and the custom rules that are proprietary and that, in a way, secret and not accessible for any user. So we see that net flow data from switch or routers is very compact, so allowing a long retention period, but it does not provide sufficient context, mainly because they are limited to L2 to L4 layers. On the other hand, the full packet capture provides the maximum level of information, of course, and of contextualized data. But it is very difficult to store for a long period of time, due obviously to the size. And both IDS and cyber sensor provide security rules to detect in real-time network anomalies, but cyber sensor provide also more context about the traffic, thanks to the advanced classification, while reducing at the same time the storage requirement by only focusing on everything that is not explicitly considered as safe traffic. So here the combination of IDS and cyber sensor provide a good coverage of known threats, thanks to the rules provided by the community, and also provide an excellent visibility on the non-alerted traffic to detect the unknown threats. So typical implementation of a cyber sensor is to work aside an IDS and feed an existing NDR system, network detection and response system. So this enriches the NDR with the benefits from the information provided by the cyber sensor and the ability for the analyst to create new rules based on the flow classification in order to detect threats that an IDS will never be able to detect due to its limited protocol coverage. So the analyst can also retrieve more context when investigating on an alert generated by an IDS. For instance, identification of the device that has generated the alert, or having the full history of all applications accessed by the device for a long period of time, in order to detect any anomaly that could explain the alert. So now let's dig a little bit more in a few concrete examples where a cyber sensor can help an IDS to detect threats. We saw that Sunburst malware was contacted with a command and control server using remote desktop protocol, RDP. The technique is listed here by MITRE as application layer protocol. So according to MITRE, this technique uses standard protocol such as HTTP, FTP, SMTP, or other email protocols, standard email protocol, which are commonly used in IT networks for basic services like emailing or web communications. So those protocols are allowed by firewalls to ensure the basic network function. So they can also be used by malware to retrieve instruction from their command and control server. Also commonly internal use protocol like SMB, SSH, or RDP may also be used when allowed outside the organization, which is more and more common because employees have to work more and more from home or any other place. So in case of Sunburst, it was RDP, the remote desktop protocol that was mainly used to contact the command and control server. So the recommendation from MITRE to detect such technique is to look for anomalies in the usage of such protocol, like upload versus download ratio, or if you see a lot of connection attempts without any success, without any response. Another method is to detect communication of such protocol between machines that have never used those protocols before, which can be done by creating alerts manually or using machine learning techniques. And another example here is to analyze the payloads to identify anomalies. So that also can raise alerts about possible command and control communication. So let's have a look how a cyber sensor can complement IDS to detect such technique. So first, for uncommon data flows, IDS are quite effective at detecting them, but usually they generate lots of false positives because the detection methods, the detection rules applies to any type of protocol, any flow on the network. So using a cyber sensor helps us to differentiate legitimate traffic, for instance, the traffic to your CRM, from unidentified application, which is not clearly identified as a safe application and not clearly in the blacklist. So only the IDS alerts from unidentified application will require further investigation. So in this case, the cyber sensor is used to reduce investigation time by helping discarding quickly all the false positive from the IDS. The second detection technique is about previously unseen communication. User endpoint behavioral analytics or machine learning rules are usually created into the NDR analytics system to cover this kind of threats. But thanks to the cyber sensor granularity of the classification, it makes those kind of rules much more efficient. Let me explain why. For instance, an IDS will consider all web traffic as HTTP. So a newly used application on top of this protocol will not be considered as a new communication because it's still HTTP. So nothing new there. But a cyber sensor will detect the application in use on top of HTTP. Is that Facebook, YouTube, whatever application. So every new application can be considered as a new communication type, and then will require further investigation to check if it's allowed, if it must be part of the whitelist or not. So here we can say that the granularity of the classification provided by the sensor is an enabler for efficient machine learning rules. And at last, the last technique is about the protocol misused. IDS are efficient for standard protocol like HTTP, FTP, or emails protocol like POP3, SMTP, or IMAP. But cyber sensor can go further and detect evasions method, such as tunneling on top of standard protocol, like tunneling on top of ICMP or on top of DNS. But it can also detect evasive traffic, a bit like an anonymizer is used, or a non-corporate VPN also, that can be natively detected by a cyber sensor, and then obviously expand the coverage of what's provided by a traditional IDS. But let's now illustrate all those concepts with a demo. So the demo platform we will use here is composed by obviously a cyber sensor, and here it's the Cosmos probe from Enea, analyzing the same traffic as Suricata IDS. So the output from Suricata and the cyber sensor are both sent to an ETL function, extract, transform, and load. And here we are using log slash from Elastic. And this ETL function is responsible for normalization of the data between the sensor and the IDS. Also is used to differentiate the local IP addresses from the external ones, and perform IP localization on external IP addresses using a Geolite database. And also it's used to create custom traffic categories like a whitelist or blacklist based on the classification result from a cyber sensor. Then this transformed data is inserted into a database, here Elasticsearch, and the visualization and dashboards are made using Kibana. So here's the result. So first, the cyber sensor provides as an exhaustive view of all your network traffic. On the top left pane here, you can see the bandwidth per protocol category. A protocol category could be email, web traffic, instant messaging, peer-to-peer, database, network protocol. So we have here a set of categories. So those kind of categories allows to quickly profile your network traffic. And then you can create easily custom rules based on your expected network usage. So for instance, if your daily email volume suddenly double, that's probably an issue. Or if you start seeing peer-to-peer traffic, so new category arriving that your firewall is supposed to block, that's also kind of alerting that are very easy to detect with a cyber sensor. This kind of categorization also allow to make a distinction between the OT and the IT traffic in order to have specific policies for each one. So here in this example, we see that we have for a total of 54,000 flows. So obviously, leading investigation on each of them is not something feasible. So it's really crucial here to have this good categorization to know what's safe and where you need to focus your detection efforts on. So, for instance, you can exclude for the analysis by just creating a few filtering rules. You can exclude all the whitelist traffic and all the, I would say, legitimate traffic. In this example, so that we see the traffic is very bad because there's still a bit of everything that you don't want to see on your network, like peer-to-peer traffic, crypto mining, anonymizer. So typically everything you don't want to see. So obviously, for security perspective, all this traffic requires further analysis and countermeasures must be taken to avoid this in order to reduce investigation time in the future. But let's come back to the Sunburst case study. Because we saw that the command and control communication here were using standard network services. And here there's a custom categories regrouping all the network services commonly used on the network. So here we see Telnet, NFS, AirSync, RDP, part of it, and all the services that are allowed on your network, the internal network services. And those ones must be closely monitored. So let's now filter and drill down on this category to have a more complete view about where those type of connections take place on your network. So here on this map, you see all the network service traffic, so from the category we've seen before, from the corporate network, and also from the public internet. So all the ones that you see on your network. So here you can consider that the internal traffic, so inside your corporate organization, can be considered as legitimate. Obviously, it's not command and control traffic; it's internal. But when this traffic goes to the internet or comes from the internet, then it must be watched closely. So let's now filter again and focus on the traffic from your corporate network to the public internet. Yeah. And here we see all the communication using network services from corporate network to the public internet. We see here now it represents 58 flows only. So less than 0.1% of your overall traffic. So then it makes investigation of those flows manageable, I would say, because all those flows are suspected to be command and control flows. So now we can get even more details about those flows. And here, if we look, for instance, only at the RDP ones, we saw that Sunburst were using this protocol, RDP. We see that the RDP protocol, RDP communication between your corporate network and the outside world are only 14 flows. And those 14 flows are only for two different IP addresses, which are 20.0.0.111 and 20.0.0.3. So if those IPs are known by the administrators because we know which employee is behind, that's fine. But if those IP addresses are not known by the administrator, that's probably because we see a Sunburst or similar in action here. So now, if we check what Suricata is reporting for those for one of those IP addresses, so here we choose 20.0.0.111. We see that indeed Suricata has detected some traffic here, but it has only been classified as TCP, nothing more than that. So the RDP, remote desktop protocol, has not even been detected here. So clearly, those flows have gone under the radar. And this is really an example that demonstrates how combining IDS and SoundSource fills the gaps to detect anomalies generated by malware. With a few clicks, with a cyber sensor, you can identify what is at risk or what could be a command and control communication, where in that case, with a traditional IDS like Suricata, it's just not possible because even the protocol itself is not detected. We can find many more examples about how cyber sensors complement IDS to detect techniques used by malware. Cyber networks and anomalies can be detected during the discovery phase, where discovery tools are using a network protocol like NetMap or are doing reverse DNS. Also ICMP to see which IP address are live and response or not. So all those protocols obviously can be discovered by a cyber sensor. For the lateral movement, remote services like RDP, so that we see for command and control, but can also be used for lateral movement, or FTP or SSH, are also used by malwares to replicate themselves on other machines. For the collection of sensitive data to be exported, it's also protocols like NFS, FTP, or SCP that are used to access those sensitive files or information. For command and control, so we see an example with RDP here, but there's many other techniques like domain fronting, for instance, or other standard network services to illegitimate servers. And for data exfiltration, which is the last step, tunneling methods can be used, or evasive traffic is used to evade all the firewalls or all the protections that you may have that would avoid the exfiltration of data. So the key component for the cyber sensor is obviously its DPI engine. And Enea DPI engine is the most widely deployed traffic intelligence software in cybersecurity. And the most important value of a DPI engine is first the scope of traffic it can detect, and the accuracy of its protocol coverage and related traffic metadata. So if we drill down a little bit in details in the value of this traffic intelligence software, we can say that visibility on encrypted traffic is becoming a key feature, because IDS only consider this traffic as SSL or TLS, but lack details about the service in use inside the encrypted channel. And that only traffic intelligence can provide this kind of visibility. Also, the detection of VPN is critical, especially the identification of the VPN provider. Most organizations use a corporate VPN, so this is fine, but the usage of external VPNs must be prevented because they present a high level of risk. So such VPN must absolutely be detected in order to be prohibited. Cyber criminals also use new techniques to anonymize their activities and fly below the radar. Anonymization can be done through the usage of proxy services, for instance, or protocol like Tor, but can also use techniques like faking protocol headers, like HTTP user agent, for instance, to avoid the traditional detection. So it is very important to detect such abnormal activities, which are constantly evolving. Tunneling techniques also are constantly evolving and having the ability to decapsulate any kind of network tunnels to have visibility on what is inside the tunnel is very important. Other techniques like domain fronting detection, traffic or file spoofing, validation of encryption handshakes are also very important techniques that are covered by traffic intelligence. And aside all those traffic classification categories, detection and identification of devices from network traffic analysis is also a game changer for threat detection. So for all those reasons, having a cyber sensor complementing an IDS is becoming crucial in extended detection and response system to protect critical infrastructures. So In summary, we can say that cyber sensors are the perfect complement to IDS to fill the existing gaps for malware detection. The Cosmos sensor provided by Enea has been developed for that purpose and helps analysts to increase the coverage of threat detection, reduce the false positive from IDS, and accelerate investigation time. If you want more details about our cyber sensor, or you would like a more specific demo, do not hesitate to contact me, and I will be very happy to set up a quick conference call and try to answer all your questions. Thanks for attending and have a good day. Bye-bye.